Good afternoon, everyone. A warm welcome to the afternoon session of 6 days FDP on Introduction to Machine Learning and Python and Machine Learning Lab. And I would like to welcome Kirtan and to start the session.
Thank you. So in morning session, we have seen the categories of machine learning. So now we are going in depth of supervised learning. Let me share my PPT. This my PPT is visible?
Yes, ma'am.
Yeah, okay. So in morning session, we have seen what is supervised learning. It means supervised learning. It mainly uses a labeled data data sets to train the algorithms and to recognize the patterns and to predict the outcomes, and we will be getting the output from it. It is also a subcategory of artificial intelligence, and it is used in variety of fields like medical, financial, share markets, military, cyber security, etc. So, what is supervised learning? It includes prediction and classifications. So it means that if you are giving the input data into a trained model with a mixture of apples and bananas, then the model will be trained to classify apples in one group and bananas in one group. So this is a supervised learning. So there are two main functional concepts are there. First one is input representation, and the second one is hypothesis class. So input representation means it refers how the data is structured and presented to a model. It means in what way you are giving the input to your training model, and the quality of input data representation, it is very important because this only input representation only is going to influences your model's ability and its efficiency and your computational level to learn and generalize. There are variety of components of input representation. So first one is features. It means that variables, it is the main property of your input data, and while choosing your features you should be very cautious how, because this is this input is going to affect your computational power of your model. So you should be very cautious while giving the features to your input. So the second thing is feature space. So actually the data set will be usually of two dimensional, that is rows into columns. So that feature space should be very cautious. That is dimensional space is considered here as a feature space. That is generally we will be considering two dimensional data, that is rows into columns. It either may be a CSV file or an Excel file or a text file. So the third thing is dimensionality. The number of features defines the dimensionality. It isn't fields. How many data in the data sets are present? It may be a thousands of data or 2 thousands of data. Uh, it may be. So high dimensional input spaces can capture more complex patterns, but if you're getting more data spaces that it is not capable of solving by the training model, then in this case it will be leads to overfitting. Or if that trained model is capability of solving 1,000 data, you are inputting only hundreds of data, then that model will be going into underfitting. So it will be affecting the computational complexities. So the next one is importance of good representation. Uh, how you can say data is represented in a well and good manner means So first, it means your data should able to capture a meaningful aspects of your problem and allows the model to learn efficiently. Like the second thing is if we are choosing the input representation as a poor means, it must be able to differentiate between the classes that will be leading to low performances. For example, if you are considering your features as a tabular data um, or anything that is number of rooms or square footage location like this, these data it should be well and good defined to um, to ensure your system with a high computational power and efficiencies. So what are the examples of input representation is, as I said, your input can be a CSV file, that is a text file, or like an image, or like a video, or like a audio, anything your data set may be. So if it is a image data means input representation should consist of the pixel values of the images and color channels or any other features that is relating to the image data all should be there. If it is a text data means it should be include a bag of words vectors, embeddings and n-grams. Okay. So and while selecting your feature types, there are many types of feature types. For example, your features may be a numerical. Numerical means there should be a continuous values such as age, prices, and temperatures, or everything will be represented as a numerical data. If it is a categorical data means you will be having a minimum unique values. For example, color representation or type of a car representation. Type of a car you can consider manual or automatic. There will be a minimum of two unique data only. So those data can be considered as a categorical values. Ordinal data means there will be a level of categories like high, medium, low, that level of categories. So text means structured and unstructured data. Like these types of features types are available. So second thing is next one is hypothesis class. The hypothesis class in supervised learning, it means a set of all possible functions. That is, it is denoted by the H. The choice of hypothesis class, it defines the types of relationship between the models uh, that is captured between inputs and you are getting output. It means that the learning algorithm can choose from approximate values that targeting the functions. In supervised learning, the main role of the hypothesis class is to find out the best hypothesis within this class that match the input data to getting a desired output data with a minimal error. It ensures that the training model should not produce the error for generating the output with the predefined inputs. Defining the hypothesis class. So there are three family classes for defining the hypothesis class. So the first one is linear models. So linear models, generally we use the linear regression model or linear classification. So these two will be consisting of the linear functions. So it can be represented as a h of x uh, with a combination of the vectors and the bias terms. So the second thing is decision trees. If you are using the decision trees, the hypothesis class includes all possible tree structures. It means the decision tree while forming a hypothesis class where each function representing a tree structured form. while that input space is divided into separate regions with different predictions, because all the inputs will not able to predict by the same cases. So this class will be handling while decision tree incorporating the hypothesis class, it will be helps to handling the non-linear relationship, and those relationships should be interpretable. But while using the decision trees may leads to have limitations in capturing smooth decision boundaries. So it is not advised to use the decision trees with the hypothesis class, because otherwise it will be producing a very critical range of efficiencies. So the next thing is neural networks. So now in all the research, this neural networks is playing a crucial role. While including the hypothesis class in neural networks, um, it is generally used for complex functions. It means that a neural network with a given predefined structure, that including the number of layers or a nodes with a broader set of nonlinear functions. While using the neural networks with the hypothesis class will be highly flexible, and it is very easy to handle more complex functions, and it is also easy to capture the intricate patterns in the data while you are inputting the data. If there is a presence of problematic representations in the data, it can be easily handled while you're using a neural network with hypothesis classes. So this is a mathematical representation of the hypothesis class. So where H is the hypothesis function and X is your input and Y is your output. Here, so where H belongs to H. This is the hypothesis function. This is a hypothesis class. So every hypothesis function should be belongs to the hypothesis class. So it means that H star is the improvisation of the best hypothesis. It means it should able to minimize the difference between the predicted output and the true output. So learning a class from the examples. So consider one example. I have represented an example, that is consider a class of a family of cars. So that there will be a positive examples and also a negative examples. How the positive and negative examples are represented using the hypothesis class, we are going to see. So see here, class C of a family car, class C of a family car, and prediction is car is belongs to your family car. You have to predict whether the car is belong to a family. So the second thing is knowledge extraction. What do people expect from this family? That is include cars present in the family. What will be your user expectations? So first thing, I have to represent the input as X1 as price. So based on these two inputs, the price of the car and the people expectation may vary. So my X1 will be belonging to the price and X2 will be belonging to the engine power. So I have to get my output as two categories, that is positive values and negative examples. That is whether the car is up to people expectation, and negative examples will be representing it means that it is not satisfying the people expectations. So the training set of the family car is considered. So the plus denotes the positive examples and minus denotes the negative examples. So this is represented as, so while considering the AND functions, so that is this P1 and P2, it means that the price of the car from minimum price to maximum price, and also the engine computation of power is from the minimum also to the maximum. So these two categories are considered by the AND function. So the prediction should be done based on both the inputs to user expectations. So now the hypothesis is at first the training set is represented as if these are minus categories and these are plus categories. So the minus categories are predicted in this. Okay. So then the prediction function will be represented as x equal to x power t comma r power t. So if there is a value of 1, if x is positive, and if x is negative, the value will be 0. So according to these values, it is represented in the x and y axis. I'm getting the training set is like this. So while representing the hypothesis class, I have to correlate the plus values within this hypothesis class, and it means that it is satisfying this function. These values satisfying this function and remaining as unsatisfying this function. It means that only 5 cars present in this class are up to user expectation level. We can conclude that. And this will be considered as a false positive, and this will be considered as a false negative. It means that this is representing the predictive models of the hypothesis class based on the engine power and prices. So it means that this will be considered as a true positive. True positive means, so these are the cars with up to the user satisfaction level. So remaining or represented falsely that these cars are up to the user satisfaction level, but according to the empirical strategy, these laws are not satisfying the user expectations. So these errors can be rectified using the error function of the hypothesis class like this. What are the importance of the hypothesis class? Why we want to go for the hypothesis class means the flexibility in this hypothesis class, it determines the model capacity into the fitting the data. If we are having the large hypothesis class, it can have the ability to capture more complex patterns, but it can leads to the overfitting model, since your hypothesis class is not having ability to solve those data, then it leads to the overfitting. It means that you have to be very cautious while choosing the right hypothesis for your input data in order to ensure a good balance between the bias and the variance. So this bias and variance are the two important powers while dealing with the trade-off mechanism in the hypothesis classes. Before going to the examples of hypothesis class, in what way you have to choose your hypothesis class as an efficient means. So first thing is bias variant trade-off. Your hypothesis class that is very too simple means it may result in very high bias. So you have to be very cautious in choosing a simple hypothesis class. Better you can go for a very complex hypothesis class in dealing with the over complex data. So the second thing is power optimization. While the complexity of the hypothesis class is increasing, it have the ability of capturing the more patterns in the data. So, however, more expensive hypothesis classes are requiring more input data and computational resources in order to prevent the overfitting strategy. So the third thing is regularization of the hypothesis class means that while regularizing your hypothesis class, it can able to control the effective complexity mechanism of your models. So examples of hypothesis class, there are 3 classes. First one is a linear hypothesis, second thing is polynomial, and third thing is neural network. Linear hypothesis class will be dealing with the linear functions, and polynomial will be dealing with the polynomial regression models, and neural network will be dealing with the neural network model architecture. That a model is well trained model that will, it means that it can be having an inclusion of hidden layers, activation functions, and weights like that. So how we are going to balance the input representations and the hypothesis class? There are 2 problems that may occur. One is underfitting, another one is overfitting. Suppose if your class is capable of processing 1,000 data, if you are inputting only the 100 data, that is also a problem. If your class is capable of solving only 100 data, if you are inputting the thousands of data, that is also a problem. So you should be very cautious in input representation and defining a hypothesis class in order to train your ML model. So in underfitting category, if you are when it will can occur means if your hypothesis class is very too limited to capture the complexity means underfitting will be occurring. If hypothesis class is also it seems to be very flexible also, it can cause to the overfitting strategy. So you have to choose very appropriate hypothesis class for an appropriate input representation. That will be a good for training a ML model. So the second thing is version space. So here in machine learning, version space, it is a subset of a hypothesis. It means that it is deriving from the hypothesis class. It is very consistent while training your data. In other words, you can represent it as a collection of all hypotheses that can correctly classify all instances of the training data. So this concept is particularly useful in a concept learning based. That means it helps in understanding the range of unseen data um, that may helpful in very solving potentially for solving a problem given by the users. What are the main key concepts of the version spaces? First thing is hypothesis class. Second thing is consistent hypothesis. Third one is version space. So the first one, hypothesis class H, it is a set of all hypotheses. It is denoted as a capital H. It means it is including all the potential models or the functions that is mapping between the inputs to the outputs. For example, if your hypothesis class is consisting of the linear classifiers, that is linear regression models, it means each hypothesis is different linear boundary in the feature space. So the second thing is consistent hypothesis. In consistent hypothesis, it should satisfy that the hypothesis should belongs always to hypothesis class is considered to be a consistent. It means if it correctly predicts the output for every example in the data set, then there is a consistency in hypothesis class exists. So the goal of consistent hypothesis is to find the better hypothesis or a hypothesis set that matching accurately of the observed data with minimization of errors. So the third thing is version space. That if you are considering the version space as V, then it is a subset of hypothesis. So that is represented here. It is a subset of hypothesis. It means that it contains all the hypothesis classes in hypothesis such that H is also consistent with the version space, that is training data sample. For example, if you are considering the hypothesis, considering the hypothesis H1 is equal to red and H2 equal to H2 equal to the object is red and this is the object is small and H3 equal to the object is red and also small, then it turns to be a positive. So this is the instance of the version space. So this is a mathematical representation. I have already said the version space should contain the hypothesis belongs to the hypothesis. It means that it is a subset of the hypothesis. So what are the properties of the version spaces? So there are two properties are there. In machine learning, there are several key properties of the version space is there. So the first thing is consistency check. It means that while you are giving the input into a model that is training data, you have to ensure there is a consistency in the training data. The version space consists only of hypothesis that are consistent with all the training examples. So that we have seen that is H belongs to hypothesis class. It should be always consistent. It means that as you are adding new examples, then the version space should retain the hypothesis correctly and classifies the previous and new examples, and it has to be checking progressively for refining the set of possible examples. So the second thing is generalization of the boundaries. So the version type is generally defined by the general boundary and the specific boundary. So there are two types of boundaries over there. One is a general and second one is the specific boundaries. So the first one is general boundary means it will be dealing with the general hypothesis. It means that it classifies the input data, but only it will be giving only few assumptions in the output data. It will not give the clarity in the assumption of the data. But in the specific boundaries, it will be containing most of the specific hypotheses, but it is very consistent along with the data, where the general boundaries it doesn't do. So next one is Wapnick Cherokee dimension, that is BC dimensions. BC dimensions. It means that it is a measure of complexity of your hypothesis class. It means it is a fundamental concept in machine learning theory, because how your hypothesis class is becoming more complex or less complex. In order to ensure the complexity of your hypothesis class, this DC dimension is needed. So what the definition is it? It means the dimension of the hypothesis class H. It is defined as a large number of points that can be shattered by the H hypothesis class. So there are two categories in there. The first one is shattering and VG dimension. Shattering means a set of points, that is a set of points are shattered on the hypothesis class if every possible labeling of these points that exists the H. VC dimension means it covers the maximum points. It covers the maximum points that are shattered within the hypothesis class. So the implications is it, and also while dealing with the shattering, for every possible way of labeling, there exists a hypothesis that is able to classify correctly according to that labeling. We want to ensure this property. So what are the implications is, if your VC dimension is high means that exists a more expressiveness of the hypothesis class, and it also increases the risk of overfitting. If your VC dimension is low, it may be causing the underfitting problem. So the VC dimension should be in the case of not lower or not higher, because this is the property of ensuring the complexity of a hypothesis class. So this is some mathematical implications of VC dimensions. So it plays a vital role in understanding the probably approximately correct learning framework we are going to discuss further. So according to the VC theory, the generalization is represented as like this, where n is a number of training data samples, and C is a constant, and dV is it is a VC dimension, and it is the accuracy of the hypothesis class. So examples of the VC dimension. So what are the examples? The first thing is linear classifiers in 2D, or we can say that linear separators in 2D. It means that, for example, it is represented in a line, right? Suppose we are representing like this. This is the linear separators of the 2D function. So for linear classifiers in two-dimensional spaces, This means the line can separate any possible two labeling of the points inside the version space. However, with the 4 points in general position means it may not be possible. Only it will be working on the two-dimensional way only. So the second thing is polynomial classifiers, or it can call as a polynomial models. And if there are higher degree possible polynomial classifiers means as they can fit more complex patterns. So that is represented as a polynomial degree D in one dimensional space that has the VC dimension of D plus 1, and it can fit as D plus 1 points in the arbitrary configurations also. So for example, as they can fit more complex patterns means higher degree polynomial classifiers will always have the higher VC dimensions. It means whether the VC dimension increases, the degree of the polynomial also increases. And there are another two examples is also there. One is a constant function, and saying the linear separators playing the crucial role in higher dimension. If it works on higher dimensions, how the VC dimension will be. So these are also the examples of VC dimensions. So what are the applications of VC dimension is first thing is model selection. So it is very helpful in selecting the models based on complexity of a given problem. It means that how to generalize a complexity of a model. Um, and also a models, if it is having a very low VC dimension means it may possibly underfit. If it is having a higher VC dimension means it may causes the overfit. So the second thing is theoretical boundaries on space complexity, on sample complexity. It means it giving the knowledge into a space complex sample complexity. What is sample complexity means the amount of data needed to ensure that the model generalizes well to a new data arrives. It means to achieve the good balance between fitting the trained data and generalizing to the unseen data. It means that labeled versus unlabeled. The number of samples should be at least the number of samples, that is, samples should be always proportional to the VC dimension. Comparison of the version space and VC dimension is version space. It is a set of hypotheses and it measures the complexity of the hypothesis. So, what is the role of these two in learning theory means? It helps in assessing the consistency of the hypothesis. It purely dealing with the complexity of the hypothesis. So, next one is fact learning. That is probably approximately correct learning. It is a framework for the of the machine learning. It is purely dealing with the mathematical analysis of the machine learning. It means that a learning algorithm can learn a concept or a model will be more efficiently or effectively. How the model is working effective and efficient, that will be dealing with the path learning. That is what is the goal of path learning is. It purely deals with the probability that is approximately correct or not. If the assume there is a no error on the data, that approximately you can say that there is no error in the data, but while training the model, there may be a presence of error in the data. What are the key concepts is, so the first one is path learning setting, that is in finite hypothesis space, and second one is probably approximately correct. So the first one is in path learning while dealing with the finite hypothesis space, so the number of training samples is represented as a m, and the gap between the training and true error occurs can be represented like this, and the complexity of hypothesis is represented like this, and it should be at least 1 minus delta deriving the confidence of the relation. So in special cases, the error of the training data may also be zero if the data is correct. If you, while this condition fails while you are taking more complex number of data, this condition will be fails. Most probably, this will be condition is getting failed because the hypothesis H has an error state means it may be it is lesser than background means there may be a chance of getting the high error rate. Probably defines this. Uh, I have said this. This is the case of probability, and with the probability at least 1 minus the hypothesis H satisfies the error requirement. So bounds of the finite hypothesis. It can be probably can be calculated like this. Suppose how many training data examples are sufficient, it can be calculated like this. For n is a number, ln is the learning samples, and if the error trained data is equal to zero, the probability of at least like this means your error should be always lesser than this training data samples. So, what does agnostic learning in ML means? So, assume that there is an error, and it should be always not equal to zero means that the target function C is not in the hypothesis space. It concludes it is a concept in the machine learning. It is an extension of a path learning. We can say like that. But in path learning, what are the limitations occurs? It can be overcome by the agnostic learning. So what are the key concepts here is that there will be no perfect assumption of the hypothesis since it may not contain a hypothesis that is perfectly fitting into a data. So what are the goals is means it has to satisfy that a hypothesis function should always present, that is should always present or that contains in the hypothesis class. It means that this function is enabling the lowest cause of errors. So there are types of errors. One is a true error or a training error. It is also known as an empirical error. It means this is the probability of the hypothesis that miscalibrates the from the distribution means this is a true error, and this is a training error or an empirical error. It is a error caused with the training data. So the finite hypothesis space can be represented like this. And error bounds are also can be written as like this. After that, the true error should also be lesser than the training error plus this linear data hypothesis. If you are taking the square root, so the final bounds will be calculated like this. So the next thing was path and learnable. So consider a class C with the target concepts or defined within the instances means a definition can be like this: a per clamable by learning L using the hypothesis yes if all the C that corresponds to the class C that in the distributions of the dimensions over the instances is represented as 0 is lesser than always is lesser than always half of the classes. It purely dealing with the polynomial probability properties. And also while dealing with path learnable is always dealing with infinite hypothesis space. Boundaries, that is bounds of infinite hypothesis space is calculated like this. So it means that despite of the finite hypothesis, there are the possible ways to handle the infinite hypothesis by the path learning. So what are the key issues while dealing with the infinite hypothesis occurs means there is a risk of occurring overfitting, that is risk of occurring overfitting and model complexity, and also the risk of occurring the sample complexity is also there. So practical path algorithms available are one is the decision trees, linear models, that is linear classifiers models, and neural networks. So all these base concepts are accordingly with path learning can be used to train your hypothesis classes. So what are the limitations of the path learning means? So the first thing is it is always dependent on error and confidence parameters. It means that it always provides the foundations for understanding when and how well a machine learning algorithm can learn a target concept, but it has a several limitations while dealing with the dependence of errors and confidence parameters. While you are setting the parameters, that always uh, belong to the data, which may not be easy to estimating the errors, and it also may not correspond to the practical needs in the real-time applications. It means if your assumption of a independent or identically distributed data, it is very difficult if any unknown distribution occurs. In many real world scenarios, the data may not be identical due to the factors like changing of the environment. For example, if you are considering the weather forecasting data, so the same forecasting data will not occurring in a subsequent year also. It keeps on changing, so there will be a temporal correlations occurrence of those data. So in real world data challenges, this path learning will not give the consistent results. Third thing is assumption of the binary classifications. So the original path framework, it is primarily addressing the binary classification problems only, while the learner or a user is attempting to distinguish between any two classes. That is, if it is a occurrence of multi-class classifications or a regressions, that may be a theoretical warrant is needed to typically strongest for binary classification. In such cases of more complex tasks, the path framework will not provide the same level of theoretical sites. So these are the limitations of the path learning. So the next thing is the noise in the data, and learning multiple classes and model selections. So these are also the important concepts that influences the training model performance, complexities, and adaptabilities. There are many types of what is the first thing is what is the noise means. Um, it is a data set. It is also a data set, uh, and it is also an entity of a data set that may be occurrence of a random or unwanted variations in the data that affecting the originality of the input data. That is a noise. It can be of many forms. And what are the types of noises? First one is a label noise. There are four types of noise. I will discuss further other types of noise also. So the first one is label noise. So label noise, it means that any incorrect labeling of the training data is available that refers to the label noise. For example, if any object is wrongly named, means for example that is cat is labeled as dog in the image data set, means it is considered as a noise here. So it also known as errors or inconsistencies of the target labels. It is purely caused by the human only, label noises. And second thing is feature noise. It is also known as an attribute noise. It is known as a distortions or any inaccuracies in the feature values, like missing or corrected data. For example, if you are containing a data set with temperature readings, some sensors might produce incorrect values due to hardware malfunctions, right? So those are considered as a feature noises. So next thing is irreducible noises. Irreducible, it is also known as a redundant features, variations in the data that cannot be removed or explained by any model, that is irreducible noise. For example, in medical data set, if you are considering patient's favorite color, that things these ML models cannot able to predict, right? So those are known as irreducible noises. Uh, Other types of noises is also there. In case of measuring process, there are two types. One is a device noise and environment noise. And in fabricating process, variation of noises, and working process, random noise and EMI noises are there. So what are the impact of noises? If noises occurs, uh, as- before going to impact, how the noises are caused means. So the first one is noise can be caused due to human error. It means mislabeling of data or data entry errors or any missing of annotations in the data. These things can introduce the noise in your training data. So the second thing is data collection issues. If a human is not able to collect correct data for fitting into a training model, so that can cause a noise. Or some environmental factors, it means like remote sensing. So these environmental factors can lead to a noise, or a data transmission errors are also leading to the noise. uh, what are the impact of noise means? These noises can lead to a overfitting problem or underfitting problem. It may lead to a decrease of the accuracy of your it may lead to decrease of the accuracy of your training model. And in case of overfitting means, if your model is trying to fit into a noise the training data means, it may lead to a overfitting or poor generalization abilities. So the next thing is complexities. So there is a chance of increasing the complexity of your trained model while the noise is present. What are the techniques to handle the noise? So the first thing is data clearing. It means that removing or correcting mislabeled examples like outliers or inconsistencies before it is going into the training model. So that is data cleaning. What are the techniques in data cleaning? We can say like outlier detections or scores or statistical methods, anything you can use for data cleaning models. There are variety of methods are available for data cleaning in order to handle the noises. So the second thing is regularization. So in regularization, if you're adding more constraints to the model, such as L2 regularization, it will prevent it from fitting the noises. It means that it earlierly stopping the reduce of risk of overfitting to the noisy data. It means that a regularization, if you are applying the regularization, it may not affect the complexity of your trained model. The next thing is noise robust algorithms. Using such algorithms like random forest or decision trees, um, which can be very less sensitive to the outliers or noise features. You can use such kind of algorithms in order to reduce the noises. So the last thing is outlier detections. Outlier detection, there is also outlier detection algorithms for detecting the outliers, and it can be helpful in reducing the noise into a models. And by using the noise tolerant loss functions also, you can reduce the noises. And semi-supervised algorithms is a very good algorithm. Is for handling the noises good than the supervised and unsupervised algorithms. So learning the multiple classes. So the next thing is learning multiple classes. uh, in many real world applications, there is a, if you are dealing with more than one classes, then it is known as a multi-class classification. and it is refers to the task of building the models that can classify the data into more than one classes. So that is also known as a multi-class classifications. If you are using the binary classification, that is two classes. If you are using a multi-class classification, that will be involvement of more than two classes. So what are the key concepts is? Sorry, what are the approaches that is common strategies is? So the first one is OVR, one versus rest. It means in this approach, the binary classifiers is trained for each class, where the goal is to differentiate that class from all the other classes. It means that if there are k number of classes, means there will be requirement of k classifiers. For example, if you're having three types of classes is A, B, and C, you have to create a classifier for A and also for B and also for C. So that is one versus rest. And one versus one means, so there are advantages of using the one versus rest. It is very simple and it is very easy in handling the arbitrary data. And what are the disadvantages is if you want to have the less computational cost for your training model, this is not suitable. You can go for one-to-one for high computational cost. It's a low computational cost. And one-to-one approach, that is OVO approach, in this, every binary classifier is trained for each class of classes. So that is, it will be resulting in the k into k minus 1 by 2 classifiers. Suppose if you are using A, B, C as the classes, and if you want to create a classifier, you can create classifier B for A, C for B, and A for C. So it will be like chaining process. So the advantages are it is more precise. So this is one-to-one is more precise when comparing to the OVR and but it is if we effective while comparing to the while coming to the efficiency, it is very high expensive and can suffer from over representations. So the next one is soft max functions. So it is commonly used in neural networks. It means the final layer of the neural network. It uses the always uses the softmax functions in order to provide the highest probability distribution for among all the classes. So the fourth thing is tree-based multiple class classification. It means that here there is a use of decision trees. It is also a multi-class direct methods. It naturally extended to the multi-class problems, as a decision tree will be having the each class like trees. Each class will be representing to each one of the classes. What are the challenges we are facing in multi-class classification means? So the first thing is imbalanced classes. Imbalanced classes means some classes that may having the underrepresentation of the data, it may leading to biased models for in the favor of majority classes. So the techniques like undersampling or oversampling, it is these methods are used for handling the class imbalances. So the second thing is error propagations. Error propagations in the methods like OVR and OVMove. So misclassifications are introduced. It means as the number of classes increases, there will be a complexity of training models also increases. It also affects the scalability of the system also. So the next thing is model selection. How you want to select your model for your training data. It means it is it is a crucial step. It is a critical process in machine learning that involves selecting a most suitable model among several models. The user's goal is to find out which model can fit into my training data. Model selection will be based on two categories. One is underfitting and overfitting. That is, bias will be dealing with underfitting and variance is dealing with overfitting. So you have to find a model that not only performs well on the training data, but also generalizes well to unlabeled data also, and also minimizing the overfitting and underfitting variances also. So it also involves choosing the right algorithm, like tuning the hyperparameters or evaluating the performances or evaluating the computational power of the models, etc. on performance metrics. So, what are the steps involved? Is the first thing you have to define the performance metrics. So, how you can define the performance metrics means first you can go for a data pre-processing, that is feature engineering and data splitting. It means that selecting the how can we say that feature engineering means for example, normalizations or and handling the missing values, like that we can say that is a feature engineering process. And second thing is data splitting. So this is having the two categories. One is feature engineering, another one is a data splitting. And data splitting means dividing the data sets into training, validation, or testing. You are going for a training or a validating or splitting, like that you have to split your data. So next one is cross validation. So cross validation, it is a technique used to evaluate the model performances by splitting the data into multiple subsets, and you have to training the model on different combinations. There are many types of cross validation algorithms like k-fold and stratified k-fold, or leave a one out cross validation, that is loop validation, like that. There are many methods in cross validation is there. So this next thing is hyperparameter tuning. It means that here the parameters are not learned in the training process, but they're set before the training begins. It means that involving of the hidden layers. It means you can tune your parameters by grid searching on random forest algorithms or patient optimizations, or you can use a genetic algorithm also for parameter tuning. So the fourth thing is model complexity and regularization. That is model evaluation. It means after you have selected your model, it is important to evaluate the complexity and regularization of your model using the various metrics dealing with accuracy, precision, recall, or effort score, like that. Based on those parameters, you have to check your complexity of your models. And what are the techniques you are carrying out for model selection is hold out validation. Hold out validation, it means that and cross validation I have already said. Hold out validation, it is a commonly used method for validating your model, like data splitting or model training a data or testing a data, like that. That is hold out validation. And how we can say an example for hold out validation means if you're having the data set of 1,000, you can randomly split that data set. 1,000 means you can split it as 800 and 200. and you can set it as a training set as 800 and test set as 200, and you can continue to training the model and you are testing the model. So for training the model you can keep the 800 data sets, and for testing the model you can keep 200 data sets. So this is holder validation. It means you are holding out the 200 instances for testing your model. So the second thing is cross validation. So cross validation I have already discussed, like a careful cross validation and satisfied cross validation. You can use it, and ensemble. Sorry. And ensemble methods means, what are the examples of ensemble methods? Means like bagging or boosting your models or stacking the models, like which for usage of these kind of models, it will improve the performance of your ML model. It means that for a XML models, a good example is a random forest algorithm. So last thing in your supervised learning is generalization. It is generalization. It deals with model's ability. It purely deals with model's ability to in order to make accurate predictions on unseen data. Um, Not just the data, it was trained on. Okay, it is a very key aspect of any successful model. You can say my model is very successful model if it gives high generalization. It is purely dealing with two factors. One is underfitting and overfitting. So what are the factors is affecting the what are the factors affecting the generalization is um, complexity of the hypothesis class. It means that if you are deriving you are taking your hypothesis class as more complex, then it will be causing of overfitting problem. If you are having your very easy hypothesis class, then it will be causing underfitting problem. So these are the factors that affects the generalization. The second thing is quality and size of the training data. You are advised to choose appropriate size of training data for your hypothesis class. So the third thing was noise and data quality. Before inputting into a train model, better you reduce the noise or improve the data quality by using a data cleaning methods and improvisation methods. So these are the factors that affecting the generalization of the model. How you can measure the generalization? The first thing, cross validation. So next, test set performance and learning curves, and what are the techniques to improve the generalization? That is, what are the techniques you can use? Is data augmentation is one of the basic technique. It is used to increase the model's generalization. It means that in tasks like image classification, if you are going for image classification, data augmentation can be used to artificially increase the size of the training set by applying. You can apply some rotations, right? The image rotation, or cropping your image, or flipping your image, or reducing the noise of your image, like that. This kind of methods can improve your generalization of your models, and dropout models in neural networks. Basically, neural networks dropout models are used. It means randomly dropping out the units during training in order to prevent the co-adaption of training data sets and improve generalization. So the third thing is pruning, data pruning. So in case of including decision tree based models, this pruning is very helpful to remove the extra branches, that is unused branches in the decision trees. So L1 and L2 regularization, it means that adding a penalty term. If you are having more underfitting or overfitting models, it means that it leads to the penalty to in order to um, increase the efficiency of the system. So these are the generalizations. Generally, in generalization, it is for achieving a good generalization, it requiring the balance, right? So it is very important. Balancing the model's complexity with your training data samples is very important in order to escape from the overfitting or underfitting models. So basic key factors that is affecting the generalization, noise is the same thing, only bias, variation, like that. These are the key factors that can influence generalization. By using these kind of techniques, we can improve the better generalization of the training models. So then here we completed the unit 1 of detailed explanations of the supervised learning and types of machine learnings in the morning session. And thank you for your patience and listening to my lecture. Any doubts you can clarify?
And also you can use chat in
Any doubts you can unmute your mic and ask, or you can ping in your chat window. Arulmali, shall we wind up?
yes, and participants, if we don't have any doubts, shall we wind up the session? Okay, ma'am, we will wind up the session, ma'am. I would
Okay.
like to thank all the participants for taking part in the session. And I would like to thank Geeta ma'am for making the session excellent. Ma'am. Thank you.
Okay. Thank you for this wonderful opportunity to share my knowledge about machine learning. Thank you, Pencil Bits.
Participants are asked to fill in the form in the chat window.